Today we'll be looking at Physics, Chapter 2, Part 2, and in this part we'll be looking at the distance time graph and speed time graph. Okay, so we'll be looking at the motion, and we'll be showing motion using the graphs. Okay, first we're going to plot the distance traveled against the time taken for that journey so that we can calculate the gradient, and the gradient of the distance time graph gives us the speed of the motion. And then we're going to plot the speed against the distance time graph and the speed against the time, so that the gradient of such graph gives us the acceleration of the journey. So without much ado, let's look at this, and let's look at our first tutorial in the distance time graph. Now in this tutorial,
this video is on the topic of interpreting distance time graphs. A distance time graph always has distance on the vertical axis and time on the horizontal axis. Here, this straight diagonal line on the graph shows that the distance traveled is increasing as time goes by. This is because speed is equal to distance divided by time, and gradient is equal to rise over run. So the speed is equal to the gradient, which is equal to the rise or the distance, divided by run or time. The distance time graph of an object traveling at constant speed will show a straight line with a gradient, so a non-horizontal line. An object moving with a faster constant speed is represented by a straight line with a steeper constant gradient. An object moving with a slower constant speed is represented by a straight line with a shallower constant gradient. An object moving with acceleration is represented by a curved line with a gradient that gets steeper. A smooth acceleration will show as a curve with an increasing gradient and no pause during the change. An object moving with deceleration is represented by a curved line with a gradient that gets smaller. This graph is split into two sections also, to show more clearly the deceleration of the car. An object at rest will have a distance that doesn't change over time, so a horizontal line. The horizontal line can be anywhere on the distance axis. Part A, where does the runner finish the race? Let's have a look at the distance axis, as this tells us information about the runner's location. At the start of the race, the runner is 0 kilometers from the start line. So the runner finishes the race back on the start line or in the same place as they started. This will give you 1 mark. Part B, how long is the runner at rest during the race? The runner is at rest when their distance is not changing, so the graph shows a horizontal line. Mark the start and end time of each rest period by drawing vertical lines with a ruler onto the graph. This gives us our first mark. We can see that each square on the axis represents 15 minutes. This means the total rest time is equal to 15 minutes plus 15 minutes is equal to 30 minutes, or our final answer. And the final mark. In Part C, which section is the runner running their fastest average speed? Here we need to compare the gradients of the three non-horizontal sections of the graph. As the gradient of the graph equals the speed of the runner, it is best to find the gradients using the whole length of each section. Draw horizontal and vertical lines to create gradient triangles for each of the three sections of the graph. Now calculate the gradient of each section. Section 1 has a gradient equal to rise 3 squares divided by run 2 squares equals 1.5. It is easier and quicker to count the squares to find the gradient. Section 2 has a gradient equal to rise 2 squares divided by run 1 square equals 2. And section 3 has a gradient equal to rise 5 squares divided by 4 squares equals 1.25. The runner runs their fastest average speed in the second non-vertical section of the graph, all between 6:45 and 7. 1 mark. Part D, what is the runner's fastest average speed in the race? From Part C, we know that the fastest average speed is in this section here. So now we need to use our gradient triangle again to calculate the actuals. Continue the horizontal and vertical lines to the axis, as this makes it easier to read the scale. On the distance axis, we can see that each square represents 2.5 kilometers. So the gradient triangle goes from 12.5 to 7.5. From part B, we know that each square on the horizontal axis represents 15 minutes. This is a quarter of an hour, or 0.25 hours. This gives us the first mark. Now use your calculator to find the speed. 20 kilometers per hour. This is for the second mark. In summary, the gradient of a distance time graph represents speed. The steeper the gradient, the faster the speed, and the smaller the gradient, the slower the speed. Objects that are stationary are represented by a horizontal line. Acceleration and deceleration are represented by gradients that change. An object accelerating has a gradient increasing in steepness, and a decelerating object has a gradient that gets less steep. Draw lines onto the graph to help work out values in the scale, and then calculate the gradient. Don't forget to check out all our other fantastic revision resources here at Save My Exams.
Okay, so we've listened to the tutorial. Let's quickly go through it. So a distance time graph is a plot of distance on the vertical axis against the time on the horizontal axis. So if we draw a line from origin, this is origin. Origin means the base starting point. Okay, so if we draw a line from origin, this means the starting point. Okay, so 0. Usually, sometimes we write 0 here from the origin. So if you draw a line here, this represents the speed. Okay, because if we calculate the gradient of the distance against time, the gradient will give you the speed traveled by the car. Okay, so this is a uniform speed, a constant speed. So depending on the values that they give, we're able to calculate using the gradient we already learned in mathematics. Okay, now let's take a look at the constant speed on a distant time graph. Okay, constant speed is just like this one that we've mentioned. This constant speed comes for like an average constant speed. Okay, if a car or a vehicle is moving slower, then it will be less steep. It will be less steep. So the gradient will be somewhere, the line will be here. If it's a fast moving car, then the gradient will be steeper. This one will be steeper. We'll take another color to show that. A fast moving car, it will be steeper, and then we will have the line following this direction. A fast moving car, we have a steeper. The word steep, S-T-E-E-P, steeper. The steeper the slope, or the steeper the gradient, the faster the speed of the vehicle, the faster the speed. So within these three, this is the slowest speed for any vehicle that is being represented by these three vehicles represented by these three lines. Okay, this is a slower speed, this is a medium speed, and this is the highest speed in this regard. Okay, that's for constant speed that you can find in a distant time graph. Now, constant speed on a distant time graph, we say if an object is moving at a constant speed, the distance time graph will be a straight line that we've shown, will be straight lines as we've shown. The steeper now depends on the faster one depends on how steep the slope is, how steep the slope or the line is. Now, if we say stationary in a distant time graph, it means that the graph will be like this. If we say stationary, it means the graph will be like this. For example, if an object is stationary in a distant time graph, it means the object must have, first of all, let's say the object move at a certain level, and then it rests. It comes to rest, maybe before it decelerates. Okay, so at this point, if it's a distant time graph, you are plotting D against time. If we are plotting D against time, at this point, then we say the object is at stationary position. We say the object is at stationary. At this point, the object is stationary, meaning it's at rest, it's not moving in a distant time graph. But if it's a speed time graph, it doesn't mean it is at rest. In a speed time graph, this will be constant speed. But in a distant time graph, it means the object is moving is at rest, it's not moving at that point. If it's a distant time graph, let's say here is 5 5 meters, and here is, let's say, 4 seconds. Here's 4 seconds. Let's say here's 2 seconds. So at this point, between this, the object is not moving, it's at rest. Is that okay? The object is at rest. Now let's move to change speed on a distant time graph. Now, if we in a distant time graph, if we have a curved line, for example, if we have a curved line, then we say the object is either accelerating or decelerating. Is either the object is accelerating. Accelerating if it's curved like this, the object is accelerating. But it will become a deceleration if the object is curved in this manner. If the object is curved in this manner, then it will become a deceleration. It will be a deceleration. So anytime we have a curved graph in a distant time graph, we say that either you say increases slope, which means increases speed. Increasing speed, when speed is increasing, it means you are accelerating. When speed constantly increases, it means you are accelerating. So this one means increasing speed. So in paper 4 of physics, when they draw a graph, they can ask you all this question. This one means the speed is increasing. This one means the speed is decreasing or deceleration. Decreasing speed means deceleration. So you can say deceleration here. You can say deceleration is taking place in this graph here. Deceleration. This is a deceleration or decreasing speed. You use the word decreasing speed or deceleration. While this one, the slope inward, this one means increasing speed or acceleration. So in a distant time graph, if they ask you to sketch a scenario where the vehicle is accelerating, you don't say, oh, it's not possible. You show with a curve. If it's a straight line, then it's a speed. It's a constant speed. If we draw a straight line here, then it becomes a constant speed. Okay, in a distant time graph. If you draw a straight line, it's a constant speed. If you draw a curve like this, it means it's an acceleration. It's an acceleration, or you call it increasing speed. The speed is increasing. When speed changes, when speed is increasing, you are accelerating. Because acceleration is the rate of change of speed. Acceleration is the rate of change of speed. That means final speed minus initial speed divided by the time taken, you get acceleration. Okay, when it slopes this way, you are decreasing speed or what you call deceleration. So in other words, to calculate the gradient, when you have a straight line graph, you simply say rise over run. Rise means the change in the vertical axis. Rise over run to calculate the gradient. Because in a distant time graph, the gradient is equal to the speed. In a distant time graph, when we calculate the gradient, we get the speed. Okay, so the rise is the change in y, delta y, change in y on the vertical axis, the distance axis, over change in you can say change in x or change in time, depending on what we are using. Rise over run, which means change in y over change in x, which is normally the gradient formula, okay, that you've learned in mathematics. The gradient m is the rise over run, or change in y over change in x. The change in y is the distance axis. Our change in y is the distance axis, and our change in x is the time axis, which means the final distance minus the initial distance all over the final time over the initial time. Is that okay? So that's how we calculate the gradient. Now let's take a look at an example with numbers. Let's take a look at this work example. Okay, we say a distant time graph is drawn below for part of a train's journey. Now the train is traveling at a constant speed. Why? Because you can see once you have a distant time graph and you have a straight line like this, then we say this train is moving at a constant speed. It means whatever object, whether it's a car, is moving at a constant speed. They say train, the train is moving at a constant speed when we have a straight line. When we have a curved line like this, it's a deceleration, moving at a decreasing speed. When we have a line curved this way, it's an acceleration. It means it's moving at a decreasing speed. Okay? Now the question is calculate the speed of the train. Calculate the speed of the train. So if you want to calculate speed, we can simply just look at the gradient. Okay? To calculate the speed, this is a a constant speed. To calculate the speed in a distant time graph, we find the gradient. So we can just draw, you can use the entire straight line to form a triangle. Okay? You can use the entire straight line, or you can use part of it. You get the same answer. So we just do this. So we know this is the highest value, the change in y. Remember our gradient, our speed is equal to gradient. Our speed in a distant time graph is equal to the gradient and is equal to the rise over run. Change in y is equal to change in y over change in x. Equals to change in the y-axis over change in x. So in this regard, we just simply say our speed is equals to, what is our change in y? The final y, the topmost value here. What's the topmost value on the y-axis? 8. So we say our speed will be calculated by simply saying 8 minus the bottom point. Because you always, remember when you want to draw a gradient, you choose 2 points. So you can choose these 2 points from here to the end, or from the beginning to this place, or just use the whole thing. So you say minus 0, okay, minus the bottom point on the y-axis, which is 0, all over the change in x side. We have 6 as the highest point here. If you trace this point down, it's 6 on the y-axis. On the x-axis is 6, and if you change this point to here, is 0. So all over 6 minus 0, all over 6 minus 0. So we have our speed will be equal to, which is our gradient, will be equal to 8 over 6. 8 divided by 6. So if we do 8 divided by 6 in decimal, you get 4 over 3, which is 1.33, right? You get 1.33. 4 over 3, you get a speed of 1.33. Now you check, it's in kilometer, right? Kilometer and minutes. Okay. There's something we can do. This is in kilometer and minute. We can either change this minute to hour. We can change it to hour. Or when we finish, we put our answer in kilometer per minute. If we don't change it, we leave our answer in kilometer per minute. So we're going to do it in both ways. Here, we say this is 4 over 3, which means 1.33 kilometer per minute. Remember, but the most appropriate thing to do is to convert to the appropriate unit. So to convert to appropriate unit, 60 minutes will be what? If we change it to hour, we divide by 60, right? If we change it 6 minutes, we divide by 60. Or we just we say 8. We say 8 over 6, right? That's what we said. So this 6, we change it to hour because it's in minutes. But this 8 is already in kilometers, so we don't need to do anything to the 8. So 6 to minutes, 6 to hour, we say 6 divided by 60. 6 divided by 60, what do we get? 6 divided by 60, what do we get? Because we want the answer in kilometers, we get 0.1, right? So we say 8 divided by 0.1. We can say 8 divided by 0.1. So 8 divided by 0.1, that will give us what? That will give us 80. Okay, so if you're doing it in kilometer per hour, you get 80 kilometers, meaning the train was moving at a speed of 80 kilometers per hour. But this is the most appropriate thing to do because you must do it in the right unit. You must do it in the right unit. So it's 80 kilometers per hour. In exam, in Cambridge exam, what they will give you is something like this. They want to see whether you know how to convert this. So all this one you convert to minute, you convert to hour, this will be 0.1. This one divided by 6, 0.1. Or, on the contrary, you just say this minus this, you get 6 at the bottom. Then you change the 6 at the bottom to hour. You divide by 60, you get 0.1, then you get 80 kilometers per hour. Is that okay? So this is what it is. This is what it is. Either you leave your answer in minutes, or you even do it in meter per second if you want. If you want to do to meter per second, this 8 kilometer, you change 8 kilometer to meter, which means you multiply by 1,000. So here you have 8,000 instead of 8 kilometer. If you want to do your speed in meter per second, then the 6 minutes you want to change to seconds, you multiply by 60. 6 times 60, you get 360, right? You get over 360 if you want to do, right? Over 360, 6 times 60 minutes, 60 seconds. So to change it to second, this is in meter, this is in second. Okay, another way. If you don't want to do in kilometer per hour, you can do in meter per second. So you divide this by this, what you get? You get 8,000 divided by 360. You get 22.2, right? We get 22.2. So this will be 22.2 meter per second. Okay? 22.2 meters per second. Or if you, another way that you can do this, you know, just now you get 80 kilometers per hour, right? The 80 kilometers per hour you got, you can convert it to meter per second. How to convert to meter per second? By saying, if you want to convert this, you say 80 times 1,000. 80 times 1,000. If you want to convert it, 80 times 1,000 over 60 times 60. You know, 1 hour means 60 minutes and 60 seconds. Over 60 times 60. Another way, okay, to change this 80 kilometers per hour, if you do this, you divide by 60 times 60. 60 times 60 means 3,600 at the bottom. Here you have 80,000 over 3,600. 80,000. You have 80,000 over 3,600. 80,000 over 3,000. Because if you multiply 6 by 6, you get 36. And you put 2 zeros. 36 and 2 zeros. That's 3,600. So if you divide this, you still get 22.2. Okay? You still get 22.2 if you divide this. So I'm just showing you the various ways. You can do it kilometer per hour, and then you change to meter per second. You get 22.2 meter per second. Okay? Whichever way you do it, it's okay. Whichever way you do it, or you start from the beginning, you convert all the units. So you get 22.2 meter per second. Is that okay? Now let's take a look at another example. Now it says a student decides to take a stroll to the park, right? They found a bench in a quiet spot, take a seat and read a book on a blackboard. Okay? After some time reading, the student realizes they lost track of time and runs home. Now a distance time graph for the trip is drawn below. So what the student did has been shown in a graph. Okay, this is a distance. This is the distance time graph. The distance they moved plotted against the time they spent. Now here we have a straight line here, which means at this point will be the speed. The gradient of this point will give the speed with which the student moved. These are the time interval, okay, from 0 to 10. Time is in minutes, but the distance is in kilometers. So it's up to us whether we convert this one later on or from the beginning. Here, the students were sitting down reading from 25 minutes. From 25 minutes, if you look at this place, it's 25 minutes. If you trace it down, here's 25 minutes because the time as this is in minutes. Between 25 minutes to 65 minutes, we have to find how many minutes was that. 60. So you say 65 minus 25, so you're going to get 40 minutes. So the students, they were resting for 40 minutes. Remember, in a distance time graph, this straight line, this horizontal straight line means your resting time. It means your resting time. Meaning the students were resting for 40 minutes. So we can convert these minutes to hour depending on what they want, or to seconds. If you want to change to seconds, you multiply by 60, you get 2,400 seconds as your resting time. If you want to change to hour, you divide by 60. If you want to change to hour, you divide by 60, you get 2 over 5, which is 0.66 hours. Okay, then here's a steeper slope. This is when they now run back home. I think they were moving at a faster speed. Now let's take a look at the question, what they're going to ask us. The first question says, how long does the student spend reading the book? How long they spend reading the book? So reading the book, they spend 40 minutes, right? We've already said that. Remember, this one was the speed when they were moving to the park, when they were strolling to the park. So when they were resting was the time they were reading the book. So how long they spent in reading the book? They spent like 40 minutes to read the book, 40 minutes. So these 40 minutes, if you like I said, you can convert to seconds. 40 minutes. If you want to change to second, you multiply by 60, you get 2,460. 400 seconds. Sorry, 2,400 seconds. This is the time they spend in reading the book. Now, which section of the graph represents the students running home? Now, running home is you can see this is a greater speed. This one is a greater speed. So C, you say C is the section showing when they were running home. C, because it's a steeper slope. A steeper slope represents a greater speed. So means this one was like when they were strolling to the park. So the speed is not so high. So C represents a higher speed, which means it could be the speed with which they were running home. Now, what's the total distance traveled by the students? The total distance traveled by the students. So for the total distance, we're going to calculate everything. Now, let's show the solution. The first one, we say 40 minutes, right? 40 minutes, because this represents 40 minutes. From the time they started, which is 25, at minute 25, from 0 to 25, they were strolling to the park. They spent 25 minutes to reach the park. Between 25 to 65 minutes, they were reading the book, which amount to 40 minutes. Which amount the total time spent in reading the book was 40 minutes. Is that okay? And then the time they strolled home was from 65 to what? To 75. If you trace this one down, to be 65 to 75. So which is 10 minutes because they ran home. They didn't spend 25 minutes any longer when they were going back because they ran. So they spent only 10 minutes. From 65 to 75 is 10 minutes. Okay? So let's see what we've said. The first part of the question we said is 40 minutes. And then the time they were reading was the stationary time when they were no longer moving. Okay? And then now let's see the next part of the question, the B. It says C, section C represents the student running home, which we have already said. Then it said the slope of the line in section C is steeper than that of section A. That's how we knew that it represents they were running home. Now the part C question says we should calculate what is the total distance traveled by the students. So we have to bring all this distance out. Okay, so we say the total distance traveled by the student is 0.6 kilometers. But we're going to find out how. The total distance traveled by the object is given by the final point on the line. And in this case, the line ends as 0.6 kilometers. Let's see where the line ends. The line ends where? This point, right? So you trace it, and that will be the total distance. Okay, you trace it in a distant time graph. If it's a speed time graph, we would have found the area under the graph in order to find the total distance. We would have found the area under the graph. But in this distant time graph, just get to the last point, trace it to the distance as is. You write there the distance, the total distance, which is 0.6. You check the unit, and you tell that it's in a kilometer. So we say it's 0.6 kilometer. So we say the total distance is 0.6 kilometer by the graph. Is that okay? Now this is the tracing, is 0.6 kilometer, the highest point. Okay, so that's for that. Now we go to speed time graph. The second part of this section. Now to do the speed time graph, we have to listen to the tutorial. Okay, we listen to the tutorial before we continue our speed time graph. Okay, so you are welcome here.
This video is about interpreting speed time graphs. The worked example shows a speed time or velocity time graph of the ride profile of a cyclist when he leaves his home. Velocity equals speed in a certain direction. The velocity on this graph is all positive, so we know the cyclist is moving away from his home, and he does not turn around and come back. We will work through each part of this question step by step. Part A. Describe the motion of the cyclist between E and F for 1 mark. Hence, the answer will require a description of one property only. Draw lines on the graph from E to the vertical and horizontal axis, so it is easy to see that the speed decreases from E to F. So the cyclist's speed or velocity decreases, which is also known as deceleration. 1 mark. The steeper the gradient of the line on a velocity time graph, then the greater the acceleration or deceleration. Part B asks, what letters on the graph the cyclist will be stationary? Also, for 1 mark, look at the graph carefully. Sections B and C and D and E are horizontal lines. On a speed-time graph, horizontal lines mean the cyclist travels at a constant speed. So the only times when the cyclist has stopped are at the start and end of the motion, where the speed is equal to 0 at the bottom of the vertical axis. So A and F are the only letters where the cyclist is stationary. 1 mark. We can see immediately that part C is going to be harder, as it requires a calculation and is worth 3 marks. Calculate the distance travelled between D and F. Remember that speed is equal to distance divided by time. So distance is equal to speed times time. How do we use the graph to calculate distance? Look at the axis on the graph. The vertical axis is speed, and the horizontal axis is time. This is equal to the area under the graph. For a speed or velocity time graph, the area underneath is equal to the distance travelled. 1 mark. Here, this area is made up of a rectangle and a triangle. The area of the rectangle is 20, which is the height, times 10, which is the width, which is equal to 200 meters. The area of the triangle is a half times base of 5 times height of 20. This is equal to 50 meters for the 2nd mark. Add the two areas together to obtain the total distance travelled between D and F. This is equal to 200 plus 50, which equals 250 meters for the final mark. Part D says to calculate the acceleration of the cyclist between C and D for 2 marks. We should immediately recognize that acceleration is the rate of change of speed, which equals the rate of change of the slope, which equals the gradient of the speed time graph. Acceleration is equal to rise over run. On a speed time graph, this equals the change in speed divided by time, which equals 20 minus 10 divided by 25 minus 20 for 1 mark. This equals 10 divided by 5, which equals 2 meters per second squared for the final mark. It is good practice to use the entire length of the line to calculate the gradient. Part E asks to describe the motion of the cyclist between A and B. This is the most difficult part of the question. The gradient of a speed-time graph represents the acceleration. Acceleration equals change in speed divided by time. By drawing a tangent to the curve at the bottom and at the top, it is possible to see that the gradient of the curve increases. This means that the acceleration increases between A and B. The 2 marks are awarded for increasing and acceleration. Draw 2 tangents to the curve to identify how the gradient changes. In summary, the gradient of a speed time or velocity time graph represents acceleration because acceleration equals the change in speed divided by time, and acceleration is equal to the rise divided by the run. The area under a speed or velocity time graph represents distance because distance is equal to speed times time. This is equal to the vertical axis times the horizontal axis. The total distance of a journey can be calculated by finding the area of each shape or section of the graph and adding them together. Constant speed is represented by a horizontal line on a speed or velocity time graph. A stationary object has a velocity of 0 on a speed time graph. Don't forget to check out all our other fantastic revision resources.
Okay, so we've seen the brief tutorial on the speed time graph. there's a difference between a distance time graph and a speed time graph. Remember in a distance time graph, if we have a horizontal line like this, we say the object is what? Stationary or is resting. But in a speed time graph, if you have a horizontal line, we say the object has a constant speed. It has a constant speed, okay? So, and then this is constant acceleration. In a speed time graph, if we have something like this, we used to say increase constant speed in a distant time graph for a straight line like this. We say constant speed. But now this is a constant acceleration. This is a constant acceleration in a speed time graph. So if we plot a speed of velocity, okay, if we plot a speed of velocity against time, this is a constant acceleration, not constant speed. But in a distant time graph, a straight line was a constant speed. This is a constant acceleration. But this is a constant speed if it's resting, like if it's a horizontal straight line. And then this is a constant deceleration. This is a constant deceleration if it's going downward in a speed time graph. Okay? So, but if it's like this, if we have any case, we have this type, we have it like this. This is what? Increase the speed, increase the acceleration for speed time graph. For a speed time graph, this one becomes increase the acceleration. So there are two things you need to say, because if you draw two tangential line, if you draw 2 points here, a point here, you draw a tangential line. Let's say you draw two tangential line, you see that it increases speed. It increases the acceleration. Okay, so here, one tangential line here, and then you do another one here. You do another tangential line. Okay, you see how this is increasing. Okay, this is an increasing acceleration in a speed time graph. Okay, but if I have it like this, if we have it like this, let's say we have it like this, in a speed time graph, if we have it like this, V is for speed, okay? V is for speed or velocity. So if we have a graph like this, this is a decreasing acceleration. This is a decreasing acceleration. Is that okay? This is a decreasing acceleration. Okay, speed will be 0 at this point, only at this point, this horizontal line. When they ask you where do you have a 0 speed, at this point, when this line touches this horizontal line, on both sides, also at this point, speed is 0. Speed is also 0 here. Every other place, speed is not 0. This is a constant acceleration. This is a constant speed, and this is going down. This is a constant deceleration. Is that okay? This is a constant deceleration. Now we move on. The steeper the slope, the higher the acceleration, okay? Or the higher the deceleration, okay? So this is it. This is a decreasing speed. This is an increasing speed in a speed time graph. This is an increasing speed, and this is a decreasing speed. Is that okay? So now let's take a look at more obtuse questions. How do we calculate the distance in a speed time graph? Since in a distance time graph, you just trace it to the distance as this, you tell the value. The highest point, you trace it to the distance. If they want the total distance, trace the highest or the final point, you trace it to the distance as this, when we are doing distance time graph. But in a speed time graph, how do we now calculate the distance traveled by the vehicle or the distance traveled? You calculate the area under the graph. Okay, you find the area under the graph. In this graph, if you start from this point 0 to this place, you have a trapezium. So you can break it to two, a triangle and a rectangle. So you find the area of this triangle, which is half base times height. The area of this one, half base times height, area of a triangle, to find the distance here. And to find this one, you multiply this rectangle by the base, which is from here, from this point to this point. Whatever value you have, the difference in the value, multiply by the difference in the value in the height. Okay, multiply by the difference in the value in the height. So the height times the base, you get the area of this one. So you add the two areas together, you get the total distance traveled. Okay, or in this graph. So in a speed time graph, if you find the gradient of this slope, this line slope, the gradient is the acceleration. The gradient is the acceleration. And if you want to find the distance traveled, you find the area under the graph. Calculate the area under the graph. You get the total distance traveled. Is that okay? Now, like we said, if you look at this one, it's half base times height. We know how to calculate the area of a triangle. Area of a triangle, half base times height. This is the base from this point, the beginning of this point to this point. Assuming here is 0 and here is 6. Let's assume values. And assuming this place is 10. This place is 10. And let's assume that this place is 14. Now let's calculate that. Now we've assigned values to everywhere. Let's calculate for this graph. Let's calculate the distance traveled, the total distance traveled in this speed time graph. Let's calculate the total distance because we've assigned values. So first of all, we'll find the area under the triangle, area of triangle. Now for this area of triangle, we say half base. What's the base of the triangle? We break it to two, 1, 2, triangle and rectangle. Now the half base, half of this, from 0 to 6 is 6. So we say half times the base of the triangle is 6. Half times 6 times, what's the height of the triangle? The height of the triangle is 10, from 0 to 10. Half of the height of the triangle is 10. So we say times 10. So what do we get? We say half of 6 is 3. 3 times 10 is 30. So we get 30. Let's assume they are in a meter per second. The speed is meter per second, so which means this is 30 meter. Okay, let's assume this speed is in meter per second. Okay, meter per second. And let's assume the time is in second. Let's assume the time is in seconds. Okay, now, so we get 30 for this one. Now let's find for this one. Let's find the area of this one. So area of a triangle we use for the triangle's triangular side. Okay, it's a trapezium. Some students might decide to calculate the area of the whole trapezium. But it's always better to break it down to minimize your mistakes. Okay, now for this one is the base times height. Now what's the base? From 6 to 14, you must find the value. Don't just say, oh, the base is 14. The base is not 14. You're going to count from here to here. From 6 to 14 is 8. Okay, if you find the difference, say 14 minus 6, you get 8. So the base for this rectangle is 8. So we're going to use 8 for the base. The height is still same as 10. So to find this, the base, you say 8 times 10. 8 times 10. To calculate the distance traveled, you say 8 times 10, which gives us 80 meters. So the total distance traveled is to add the distance traveled within the triangle and the distance traveled within the rectangle. So the total distance will be, distance total will be our distance within the triangle and our distance within the rectangle. The distance we cover within the triangle is 30 meters. Within the triangle is 30 meters, plus the distance that the object cover within the rectangle is 80 meters. So we add them together, we get our total distance traveled. So we do this, we get the distance t equal to 110 meters. Okay, the distance traveled will be 110 meters by this object. Okay, so this out in the speed time graph, they ask you to calculate the distance by the object. You have to calculate the area under the graph. Okay, if the graph is a trapezium, you can either break it into triangle and rectangle and calculate each one and add them together, or you use the area of a trapezium to do the whole of this, which is, if you're doing trapezium, you're going to get the same answer, which is half AB times H, A plus B times the height. Remember the area of a trapezium, right? The formula for area of a trapezium. Okay, times the height. Okay, you use it to calculate the total distance traveled. So you can just key in your value, which is half times the A is this distance, this shorter one, which is 8. So you say half into 8 plus, you add the longer distance. The longer distance is 14. All the way from 0 to this way is 14. So you add it to this one. Then you multiply by the height. The height is same as 10. So times 10. Okay, if you want to do it all at once. But it's always better to break it to minimize error. So you say this time, this plus this, you get 22. So half of 22 is 11. Half of 22, you get 11. 22 times half, you get 11 times 10, you get 110. So you see, times 10, we get 110. So we get the same answer. For the distance, 110 meters. Okay? However, like we always encourage the students, because there are some cases where you will make mistakes. So always break them and do them individually. Let's move on. Okay, so that's it. And sometimes you have a scenario where you have a speed time graph, whether they say velocity or speed is the same thing in this regard. Okay, so there are scenarios where you have three phases, 1, 2, 3. So you have here you have you call it 1, area 1 of a triangle. Here you call it 2, here you call it 3. So you do each one, you add all the answers together to get the total distance. Okay. If they want the acceleration between this, they will tell you from here to here, acceleration from 0 to 4 seconds. Let's say here is 4. Let's say here is 4, and here is 10, and let's say here is 14, for example. Okay. And if they want the acceleration in the first 4 seconds, you calculate the gradient here, the gradient. Let's say here is 20, for example. Calculate the gradient. So to calculate gradient for this line, the acceleration in the first 4 seconds, meaning you're going to calculate the gradient of this line. Now the gradient is the acceleration. The gradient is the acceleration. Gradient equal to acceleration, which is equal to 20 minus 0. This 20 minus 0, the vertical, the rise. 20 minus 0, so I just write 20 over the run, which is 4 minus 0, which is 4. 4 minus 0, which is 4. So 20 divided by 4, we get 5 meters per second square. You must remember the unit of acceleration, 5 meters per second square. Okay, we get 5 meters per second square. Okay, so let's move on quickly. So there are different scenarios and different conditions. Here, let's take a look at this question. The speed time graph below shows a car's journey that lasts for 160 minutes or 160 seconds. Look at it. This is in meters per second and the time is in seconds. Now let's see what questions they're going to ask us. They calculate the total distance traveled by the car on this journey. They just want the total distance. So what do? You break it down. Let's break it down. And calculate the area under each of them. Okay. Break this one down. Here you're going to have about 4 shapes, and you calculate each one. Okay, I just show you, and then you pause this video and complete it yourself. Okay, so you have here, you have a rectangle here. You have a triangle here, which is same as this. So you can find one, multiply the answer by 2. Another triangle here. So you can do, because they have 2 boxes, same 2 boxes, if I'm not mistaken, same 2 boxes. So these 2 triangles look same. So if they're same, you just do 1, multiply the answer by 2. Then you also bring this one down, where it touches the graph. Take this one, is it touching here? No, somewhere here, right? Okay. From accuracy, I think you bring it down here. You have another rectangle. And then you have the last one, triangle. So how many? You have 1, you have 2, you have 3, you have 4, you have 5, you have 6, you have 7. Okay, if you don't want to break it like this, it's because it's too a lot, you can break this one as a big triangle, right? From here. The whole of this, we treat it as one entity, the whole of this one. Break it from here. Let's use a different color. We treat it as one entity to simplify our problem so that we will not be doing so much. We break the whole of this as one triangle. The whole of this as one triangle. Is that okay? We break this one as the whole of this as one triangle, and then this one as one triangle, and then this one up to this place as one rectangle. So I can call here 1. I call the whole of this one 2. I call this one 3. I call this small one 4. So we break it to 4. And we'll be able to do, and we'll find the total distance traveled. For this one, half base times height. The base is 40. From 0 to 40 is 40. Half of 40 is 20. 20 times, what's the height? Between 50 and 20, what's the middle? 70.5, right? The middle number between 50 and 70.5. So we say 70.5 times times 20. Times 20. So whatever we get the area of this one. Is that okay? Times 20, we get the area of this one. So we say half, because we just do it without like writing the formula anymore. I presume you know the area formula. So half of 40 is 20. 20 times 70.5, what do you get? 20 times 70.5, what do you get? 300 and what? What do we get? 350. Okay, so we have 350 meters. This is the distance traveled within this place. Now let's see this one. From 40 to between 80, halfway between 80 and 100 is 90, right? So here is 90. 40 to 90 is 50. So this base is 50. This base is 50, and the height is still 70.5. So let's find the area of this one. We say 50 multiplied by 70.5. 50 multiplied by 70.5. What do you get? 50 multiplied 50 multiplied by 70.5, we get 875. 875. So here we get 875 meter. 875 meter. Okay? 875 meter. Let's do the big one. This big one, we have the base from 90 to 160. 90 to 160 is 70. So here the base is 70, right? We have 70. The height is what? 25. The height is 25 for this one. So half of 70 is 35. Because the formula for area is half times the base times the height. So 35 multiplied by 25. 35 multiplied by 25. What do you get? 35 multiplied by, we get 875 as well. 875 for this one. 875 meter. 875 meter for this one as well. Okay. Now this small one is what is remaining. So can we find the base is from here? Here is what? If here is 60, here is 80, here will be 70. This base here will be 70.70, this point, and it ends at 90. 70 to 90 is 20. So the base here is 20. The base here is 20, and the height from 70.5 to 25. 70, the difference. 25 minus 70.5, what do we have as the height? 25 minus 70.5, you're going to get 7.5, right? So we get 7.5 as our height. Our height is 7.5. Our height is 7.5. So now find the area of this small triangle. The area will be half times 20, right? The base is 20. Half times 20, which is 10. Half times 20, which is 10, times 70.5 and times 7.5. So 7.5 times 5. Half of 10 is 5. 5 times 7.5, we get, divide by 2. Half times, okay, sorry. Here was 20, right? We already half it. So if you halve it, here was 20. If you half it, you get 10. You get 10. 10 times this, you get 75. So we get 75. The small one, we get 75 meters. So the total distance traveled is to add everything together. Now here we have 75. Here we have 75 meters. Okay, this small triangle, we have 75 meters. So there are 4 things to add. 350 meters plus 875 plus 875 plus 75. Okay, what do we get? The total distance. Okay, we write the total distance is equals to 350. We say 350 meters. Okay, in Cambridge, in case you find something like this in the exam, 350 plus 875. This one times 2, okay, or you just write them separately. 875 plus another 875 plus another 875 to calculate the total distance, plus another 875 meter plus 75 plus 75 plus 75. We get our total distance traveled. Okay, we add everything together. Probably, if we don't make mistake, we get 2,175. So the total distance will be in meter, will be 2,175 if we didn't make mistake. Okay, except we made mistake somewhere along the line. Okay, meter. Okay, so this is how you calculate the total distance in a journey. You break it and you do step by step, and it's way much easier. So this one, they break it to many places, okay, as it were. They break it to many places as it were, and so on and so forth. Okay. So at the end of the day, we should get the same answer, no matter how many times they break it. We get 2,000. We should get the same answer. So you see, we got the same answer, 2,175 meters as the total distance traveled by the object. So with this, we come to the end of our today's class. Thank you for joining us.